A roofer's 13-meter ladder is placed against the wall of a building with its base on lower ground. The top of the ladder slips down the wall as the bottom of the ladder slips away from the building at a rate of 5 meters a second. At what rate is the top of the ladder moving when it's 5 meters from the ground? At what rate is the area of the triangle formed by the ladder, the wall, and the ground changing when the top of the ladder is 5 meters from the ground? And what is the rate of the change of the angle formed by the ladder and the ground when the top of the ladder is 5 meters from the ground? Okay, let's start off with A first. You can pause here if you want to solve first. Okay. First step that we want to do is to draw a diagram. So let's draw a super simple diagram. Here's our ladder. This blue part's gonna be our wall, or the distance between the top of the ladder to the ground, and the green part's gonna be our ground. We're given that this is a 13-meter ladder, so 13 meters. We're given that the bottom of the ladder is slipping away from the building at a rate of 5 meters a second. And we're given that we're trying to solve the problem when the top of the ladder is 5 meters from the ground. Cool. And since this is a right triangle, I should probably do that in white. Since this is a right triangle, and we know two sides of the triangle, we can find out whatever this green side is by using the Pythagorean theorem. So we can do a squared plus b squared is equal to c squared. C is the hypotenuse, so we have 169 minus 25 is equal to this green part, which will designate as A. We have 144 is equal to a squared. So therefore, A is equal to 12 meters. And we have everything we need to know to solve. So let's start off with A. At what rate is the top of the ladder moving when it's 5 meters from the ground? Okay, so from the nature of this problem, we can already tell that this is a related rates problem. And in related rates problems, you're always, I literally haven't found a situation yet where we don't do this. You always take the derivative of whatever you have with respect to time. So keep that in mind. We're going to take the derivative with respect to time always. So we're trying to figure out what the rate of the top ladder is going. So our next step is to write down an equation that represents our situation. So we can use Pythagorean's theorem again we can use Pythagorean theorems again to represent our situation. So we have a squared plus b squared is equal to c squared. And then since we want to know the rate, we're going to have to take the derivative. And remember that we have to take the derivative with respect to time. So we have derivative with respect to time of a squared plus b squared is equal to the derivative with respect to time of c squared. Now here's where you want to be careful, because you don't want to take the derivative of things that you don't have to take the derivative of. And what do I mean by that? Our thing that we don't have to take the derivative of is c squared. Why? Because this is c, C is always going to be constant because C represents the length of the ladder, and the ladder's length never changes. It just falls down. It's always going to be 13 meters. So C is going to be constant, so the derivative of a constant is just 0. However, for A and B, we know that A is always changing. We're literally given like what the rate of change of A is right here. We also know that B is always changing because B is going to be decreasing as the top of the ladder decreases. So that means we can take the derivative of A squared and B squared. So when we take the derivative of A squared and B squared, hopefully you know how to implicitly differentiate. You get 2A times dA over dt plus 2B times dB over dt. Cool. And since we want to know the rate, what rate the top of the ladder is moving, we know that this blue part represents the top of the ladder because the blue part just represents the distance of the top of the ladder and the ground. Since we know that the blue part represents that, we're going to have to solve for dB dt. So this is the term that we're super interested in. So now what we're going to do is plug in everything and isolate dB dt because that's going to be our answer. So thankfully we do know everything. So you have 2 times A, which is just 12 meters, times derivative of A with respect to time, which is 5 meters a second, plus 2 times B, which is 5 meters, and we're solving for derivative of B with respect to time, is equal to 0. And then we can just do some simple algebra. So we can simplify this first. This is going to be 120 square meters a second, plus 10 meters times derivative of B with respect to time. That's going to equal to 0. Subtract both sides by negative 120. Subtract both sides by 120 square meters. We get, scrolling down for more space, we get 10 meters times derivative of B respect to time, negative, let me do that in a different color, negative 120 square meters. Divide both sides by 10 meters to get our final answer. Of negative 12 meters a second. There's our answer for part A. Cool. Now let's do part B. Part B is over here. Okay. Part B is asking for the rate of change of the area of the triangle formed by the ladder, the wall, and the ground when the top of the ladder is 5 meters from the ground. So first off, let's start with an equation that will represent this situation. It's asking for the rate of change of the area, so it's probably a good idea to do the area formula. The area of a triangle is 1/2 times A, which is the base of the triangle, times B, which is the height of the triangle. I guess I guess A is the height of the triangle, and it doesn't really matter. It's just a matter of semantics. And then, since we want to know the rate of change of the area of the triangle, we're going to take both sides, the derivative with respect to time of both sides. Let me fill in everything. Derivative of area with respect to time is just derivative of area with respect to time. And then the derivative of this, according to the product rule, is, let's see, should be derivative of A with respect to time times B plus A times derivative of B with respect to time and then yeah, at this point we can just plug and chug. So derivative of area with respect to time is 1/2 5 meters a second 5 meters plus 12 meters, or yeah, 12 meters a second. Excuse me, let me do that in green. Okay, this is kind of embarrassing. Wait, hold on. Do that in green. Okay, sorry. 12 meters a second times the derivative of B with respect to time. We solved that in the last problem, so we know that derivative of B with respect to time is going to be -12. 12 meters a second. And then just arithmetic. I'm not going to work through all that calculations, all that arithmetic. What you should end up with is -119/2 square meters a second. There's your answer for part B. Okay, final part. Let me scroll down for some space for part C. It might be a little annoying to scroll back up again, but we'll make it work. It's asking what the rate of the change of the angle formed by the ladder and the ground is when the top of the ladder is 5 meters from the ground. So it just we'll denote this angle as theta. They want us to figure out what the rate of change of theta is. So let me just redraw this diagram real quick so we don't have to freaking go back and forth between that. I forgot what this was. 13 meters, 5 meters, 12 meters. Okay. 13 meters, 5 meters, 12 meters. This is going 5 meters a second. And this is theta. Okay. So how are we going to write an equation that can relate theta, that relates theta? What we can do, since this is a right triangle, we can just do a really simple trig ratio. So our trig ratios is SOHCAHTOA. I'm gonna do cosine. For this problem, I'm gonna use cosine theta. I think it would work if you do sine theta, but yeah. You can do sine theta, cosine theta. You can probably do tangent of theta, but that would probably be like overly complicated. So I would just do sine theta, cosine theta. I'm going to do cosine theta. Cosine theta is equal to adjacent over hypotenuse. So adjacent is this. So we have 12 meters. Hypotenuse, 13 meters. I should probably... Okay, hold on. Give me a second. Excuse me. I'm gonna rewrite this so that we can actually freaking use it. It's not a constant. So this is A, this is the hypotenuse. So we can rewrite this as A over the hypotenuse, which is 13 meters, since that's always going to be constant. It's always going to be 13 meters, but A is going to be changing. And then we can take the derivative with respect to time of both sides. And then I'm going to rewrite A over 13 as 1 over 13 times A. So it's easier. And then just differentiate. So the derivative of cosine theta is negative sine theta times derivative of theta with respect to time. And that's going to be equal to 113 times derivative of A with respect to time. And then we want to know the rate of change of theta, so we have to isolate this. So we have to divide both sides by negative sine theta. So let me write that better. So the rate of change of theta is going to be equal to 1 over 13 times derivative of A with respect to time over negative sine theta. But the problem is that we don't know what sine theta is. But we can easily figure out what sine theta is using our trig ratios again. So sine theta is opposite over hypotenuse. So sine theta is equal to 5 over 13. Let me write that a little neater. 5 over 13. So then we can just plug in this into this. So we have derivative of theta 1 over 13 blah blah blah, fill in the rest, times negative, don't forget the negative 5 over 13, and then we can just plug and chug. So plug in 5 for derivative of A with respect to time. Uh, 1 over 13 times 5 is 5 over 13. Divided by negative 5 over 13 is going to be just negative 1. So therefore, d theta dt is equal to negative 1. And what's going to be our units? It's an angle. So it's going to be radians per second. And there we go. FRQ done.